There's something in this room right now that's lying to you. Not dramatically, not in a way that matters for survival, but physically, precisely, provably lying. Find something metal near you, a key, a spoon, a doorknob. Touch it. Cold, right? Now touch something wooden, a table edge, a pencil, a door frame. Warmer. Here's the thing. If both of those objects have been sitting in the same room for any length of time, they are the same temperature. Both at room temperature, roughly 20 degrees Celsius. The temperature difference between the metal and the wood is essentially zero. Your hand is not measuring temperature. It's measuring something else. And your brain is interpreting that something else as cold or warm with complete confidence and complete incorrectness. This is a story about heat flow, quantum mechanics, free electrons, and a nervous system that was tuned by evolution in a world that didn't contain polished copper. Start with what your skin is actually doing. Your skin contains thermoreceptors, specialized nerve endings sensitive to temperature change. There are different types. Some respond to cooling, some to warming, some to extreme heat or cold that triggers pain. They're distributed across the skin surface, more densely in some areas than others. Here's what they don't do. They don't measure the equilibrium temperature of an object. They can't. A thermometer measures equilibrium. You let it sit in contact with something until the temperatures equalize, and then you read the result. Your skin never sits still long enough in the relevant sense. What your thermoreceptors actually report is the rate at which heat is flowing into or out of the skin surface. When something pulls heat out of your skin quickly, a large sustained heat flow from your hand into the object, the receptors fire in a pattern the brain interprets as cold. When something pulls heat out slowly, a small, gentle heat flow, the receptors produce a pattern the brain reads as warm or neutral. When something pushes heat into your hand, when the object is warmer than your skin, you feel warmth or heat. Your hand is a heat flow detector, a rate of thermal exchange sensor, not a thermometer. And this is why the metal doorknob and the wooden door frame feel different at the same temperature. The metal pulls heat away from your skin rapidly. The wood pulls it away slowly. The rate of heat flow is different. The sensation is different. The temperature is the same. The property that determines how fast heat moves through a material is called thermal conductivity. It's a number, measured in watts per meter per Kelvin, that quantifies how efficiently a substance transports thermal energy. Look at the numbers and the range is astonishing. Copper, around 400 watts per meter per Kelvin. Aluminium, 205. Steel, somewhere between 15 and 50 depending on the alloy. Wood, 0.1 to 0.2. Air, 0.025. Copper conducts heat roughly 2,000 times faster than wood. 2,000. That's not a modest difference. It's the difference between a substance that barely moves thermal energy and one that moves it with extraordinary speed and efficiency. When you touch a copper surface at room temperature, here's what happens physically. The skin at the contact point is at body temperature, around 37 degrees Celsius. The copper beneath the surface is at 20 degrees Celsius. Heat flows from high temperature to low. That part is standard thermodynamics. But in copper, the heat conducts away from the interface so rapidly that the copper surface barely warms. The temperature gradient, the difference between your skin and the material it's touching, is maintained. Heat keeps flowing. Your skin keeps losing thermal energy to metal that stays cool relative to you. The sustained heat loss is what the thermal receptors register. The brain says cold. In wood, the opposite. Wood conducts heat so poorly that the wood surface in contact with your skin warms up quickly. Within fractions of a second, the interface temperature is close to your skin temperature. The gradient collapses. Heat flow slows to nearly zero. Your skin isn't losing heat anymore. Thermal equilibrium at the interface. The brain says neutral, warm. Same room, same air temperature, same object temperature. The physics of heat transport, thermal conductivity, is entirely responsible for the difference in what you feel. Now here's the part most explanations skip, and it's the part that makes the whole thing satisfying. Why does metal conduct heat so well? Why do copper and aluminum move thermal energy 2,000 times faster than wood? The answer is quantum mechanics. Specifically, it's about electrons. In metals, electrons are not bound to individual atoms. In a chunk of copper, the outermost electrons of each copper atom are delocalized. They don't belong to any particular atom, but move freely through the entire material. You have on the order of 10 x squared and 30 free electrons per cubic centimeter in copper, all mobile, all able to move through the lattice. This is what makes metals electrically conductive. Free electrons respond to an electric field. They flow, and we call that current. Same electrons, different context. Now apply that to heat. When you heat one end of a copper rod, you're giving thermal energy to the material at that end. In a non-metal, that energy has to propagate through the lattice as vibrations, waves of atomic motion, called phonons, passing from atom to atom through their bonds. This works, but it's slow. It requires the mechanical coupling of one atom to the next, and it scatters easily off defects and irregularities in the structure. In metal, a much faster channel exists. The free electrons near the hot end absorb thermal energy. They move faster. They collide with electrons elsewhere in a material, redistributing that energy. They travel rapidly across the material, carrying thermal energy with them. The electron gas acts as a heat distribution network. It's enormously more efficient than phonon propagation alone. This is why metals are thermally conductive. The free electrons, the same ones responsible for electrical conductivity, do most of the thermal transport work. Wood has no free electrons. It relies entirely on phonons. The difference in thermal conductivity between copper and wood is fundamentally a difference in quantum electronic structure. The band structure of a material, the quantum mechanical description of how electrons are organized, determines whether free electrons exist. In metals, the valence band overlaps with the conduction band. Electrons can be free. In insulators like wood, there's a large band gap between the filled valence band and the empty conduction band. Electrons are stuck. No free electrons. Slower heat transport. You felt the difference between those two quantum structures when you touched the doorknob. In 1853, two German physicists, Gustav Wiedemann and Franz, noticed something. They were working long before quantum mechanics, long before anyone understood electron structure, long before the Fermi-Dirac distribution existed as a concept. But they noticed, good electrical conductors are also good thermal conductors. And when you take the ratio of thermal conductivity to electrical conductivity for a metal, you get roughly the same number for all metals at a given temperature. This is the Wiedemann-Franz law. At the time, it was just an observation, a pattern in measurements with no explanation. The explanation had to wait for quantum mechanics. When you work through the quantum mechanical theory of electrons in metals, applying the Fermi-Dirac statistics that Dirac developed, modeling electrons as quantum particles obeying the Pauli exclusion principle, calculating how they transport energy, you find that the ratio of thermal to electrical conductivity is exactly what Wiedemann and Franz measured. And it equals the Lorentz number, a specific combination of two fundamental constants, the Boltzmann constant and the electron charge. Fundamental constants, not adjustable parameters. The ratio is what it is because of the deep mathematical structure of quantum mechanics. The same entity, the free electron, carries both electrical current and thermal energy. The ratio between how well it does each is fixed by quantum mechanics. What does this mean practically? When you feel cold touching a metal doorknob, you are, indirectly, without knowing it, sensing the same quantum property that allows the doorknob's material to conduct electricity. The thermal sensation in your fingertip and the electrical conductivity of a wire are two manifestations of the same underlying fact: free electrons in a quantum mechanical sea. Now I want to add one more layer, because thermal conductivity alone doesn't fully explain the first instant of touch. When you first make contact with a surface, what dominates the initial heat flow isn't just conductivity, it's a quantity called thermal effusivity. Effusivity combines three properties: thermal conductivity, heat capacity, how much energy a material can store per degree of temperature change, and density. High effusivity means the material can absorb a lot of heat quickly from your skin. Low effusivity means it absorbs heat slowly and its surface temperature rises rapidly toward your skin temperature, cutting off the heat flow. Metal has high effusivity. Your skin touches it, the metal surface draws heat in rapidly, and the temperature at the interface stays low. High effusivity, cold sensation. Wood has low effusivity. Its surface temperature rises quickly toward your skin temperature. The heat flow stops fast and the sensation is warm or neutral. This matters because it clarifies something. What you feel isn't just about how fast heat moves through the bulk of the material. It's about how aggressively the surface can take heat from you in that first moment of contact. Effusivity is the quantity your thermoreceptors are most directly responding to. And this explains some interesting edge cases. Aerogel, a silica material with an extraordinarily open, porous structure, has thermal conductivity even lower than wood. Touch aerogel and it feels like almost nothing, like touching slightly cooler air. Its effusivity is so low that the surface immediately equilibrates with your skin, and heat flow is negligible. Carbon fiber has moderate conductivity, but high density and specific heat arrangement. It can feel colder than its conductivity alone would suggest. The sensation your nervous system produces is a sophisticated integration of thermal physics, happening at and beneath the surface, compressed into a single percept: cold, warm, neutral, that tells you what the brain has decided about the thermal properties of the object, not its temperature, its thermal aggression toward your body. Here's the part that I find most interesting: not the physics alone, but what the physics says about perception. Your nervous system evolved to detect thermal threats, to distinguish surfaces that will damage tissue, surfaces that are too cold or too hot, from surfaces that are safe. A metal at -10 degrees Celsius and a metal at 20 degrees Celsius both have high thermal conductivity. But only one will cause frostbite. The system needs to respond differently to them. And it does, because at -10 the heat flow is much larger and more sustained. At room temperature, the system still detects the high conductivity of the metal. The signal is the same type, rapid heat loss, as the signal from something genuinely cold. The brain classifies it as cold because in essentially every natural context that classification existed in, rapid heat loss from the skin meant the object was below body temperature. The inference was correct, almost always. Before humans processed metals, before copper and iron and aluminum were refined and machined into smooth surfaces, there were no naturally occurring objects with the thermal effusivity of polished metal. Rocks are moderately conductive. Wet ground is somewhat conductive. But nothing in the natural pre-industrial environment produces the rapid, sustained heat extraction that smooth metal does at room temperature. The nervous system was never calibrated to distinguish between these two scenarios. Object is cold and object is highly conductive but at room temperature. They were, in the environment the system evolved in, the same scenario. The metal doorknob is an engineered object with properties that have no natural precedent, and the perceptual system handles it with a heuristic that was perfect for millions of years and is now confidently wrong. What you're experiencing when metal feels cold is evolutionary epistemology, a knowledge-producing system that generates accurate beliefs about the world using heuristics tuned to a past environment. Encountering a present environment the heuristics weren't designed for. The brain is doing physics. It's just doing physics calibrated for a world that no longer fully exists. I want to bring this back to where it belongs. The temperature of the metal doorknob, 20 degrees Celsius, is a fact about thermodynamic equilibrium. The feeling of cold when you touch it is a fact about quantum electronic structure, phonon physics, neural signal transduction, evolutionary history, and the brain's model of the physical world. These aren't competing explanations. They're all simultaneously true at different levels of description. Dirac found deep satisfaction in the moments when a simple empirical observation turned out to reflect fundamental mathematical structure. The Wiedemann-Franz law was exactly that, an 1853 measurement of metal properties that turned out, 70 years later, to be a direct fingerprint of quantum mechanics. A ratio between two measurable conductivities that equals a combination of fundamental constants. The kind of thing that, when you derive it from first principles, makes you feel that nature has been consistent all the way down. The cold doorknob is one of those moments. A sensation you've had thousands of times. Unremarkable. Expected. So ordinary that it never prompted a question. And inside it, free electrons, described by Fermi-Dirac statistics. Phonon transport, limited by band structure. Thermal effusivity dominating the first instant of contact. Thermal receptors reporting heat flow rate rather than equilibrium temperature. A brain making an inference from that rate that was exactly correct for the entire evolutionary history of the species, and is now technically wrong in a room with metal fixtures. The world is like this everywhere. Every ordinary thing, examined carefully, goes all the way down. The doorknob was always doing quantum mechanics. You were always feeling it. Nobody thought to ask why, until now.